Welcome back, Junior Techs, to today's explainer. We're going to be mastering the dark arts of engine diagnostics by focusing entirely on a system that is, well, incredibly simple, but honestly, widely misunderstood. I'm talking about the Positive Crankcase Ventilation, or PCV system. So grab your notepads, because we're going to break down exactly how this closed-loop circuit operates, how it fails, and most importantly, how to properly diagnose it right there on the shop floor. Okay, let's kick things off with a pretty hard truth. A $2 stuck valve can absolutely destroy a $10,000 engine. Literally. I want to hook you guys right away with just how high the stakes are here. We're talking about a super cheap, completely overlooked piece of plastic that, if you neglect it, can cause catastrophic internal engine failure. It is not just an emissions device, all right? It's a vital engine health and survival mechanism. Here is our shop syllabus for this explainer. First, we'll look at the silent engine killer. Then, how the PCV breathes. After that, turbochargers and boost pressure. Followed by field diagnostics and testing. And finally, we'll wrap it all up with service intervals and replacement. Let's get into it. Section 1. The silent engine killer. So, let's look at what actually happens inside the crankcase when things go horribly wrong. The sheer destructive chemistry going on inside a neglected engine is just wild. Look, every single time a cylinder fires, a tiny amount of high-pressure combustion gas, we call that blow-by, slips right past the piston rings. And this gas, it is packed with unburned fuel, water vapor, and nitrogen oxides. If the PCV system fails to sweep those gases out, we get what's known as acid-sludge synthesis. Basically, as temps go up and down, that trapped moisture condenses and chemically reacts with the trapped gases to form highly corrosive nitric and sulfuric acids. No joke, these acids will literally eat away at the hydrodynamic bearings and completely destroy your engine oil's longevity. It ruins its ability to lubricate, just turning everything into this thick, opaque sludge. Now, the absolutely crucial point here is knowing what this failure actually looks like when a car rolls into your bay. When that $2 valve gets stuck closed, all that blow-by pressure has literally nowhere to go, right? So it overpressurizes the crankcase. That pressure is going to physically distort and blow out the weakest oil retention barriers. We are talking blown rear main crankshaft seals, leaking valve cover gaskets, and leaking front timing cover seals. Oh, and if you unscrew the oil cap and see this milky, mayonnaise-like oil, yeah, don't make a sandwich. That is heavy moisture condensation. Unburned fuel vapors will also dilute the oil, totally destroying its viscosity. So if you're seeing these signs, you aren't just looking at a bad seal. You're almost certainly looking at a choked PCV system. Moving right along to Section 2, how the PCV breathes. To actually diagnose this system, you first have to understand the dynamic relationship between intake vacuum and the internal tapered pintle of the valve. It's a brilliant piece of engineering when you think about it, because the core challenge is this. Blow-by gas volume is at its highest when the engine is under heavy load, but the intake manifold vacuum, which powers the whole system, is actually at its lowest. So the PCV valve uses an internal, spring-loaded tapered pintle to balance this out across 4 distinct fluid dynamic states. First up, engine off or backfire. At zero vacuum, the spring pushes the valve completely shut. This is a critical safety feature. It stops an intake backfire from shooting into the fuel vapor-filled crankcase and causing a massive explosion. Second is idle. Here we've got maximum intake vacuum. That extreme suction pulls the pintle deep into the housing, choking the orifice down to minimal flow. If it didn't do this, the engine would have a massive vacuum leak and lean misfires. Third, cruising. The vacuum drops to a moderate level, the spring pushes back a bit, and we get a mid-range flow that perfectly matches normal blow-by production. And fourth, wide open throttle. Vacuum drops to near zero, so the spring pushes the valve wide open for maximum flow. If the blow-by exceeds the system's capacity here, it actually uses reverse flow ventilation, sending those excess vapors backward up the fresh air tube and right into the main air box. All right, Section 3, turbochargers and boost pressure. Now, let's talk about why adding a turbocharger completely changes the rules of crankcase ventilation. It's a whole different ballgame. If we contrast standard PCV designs with turbocharged systems, you'll see why. A standard naturally aspirated engine operates entirely in a vacuum state relative to the intake manifold. But when you slap a turbocharger on there, you are forcing positive boost pressure directly into the intake manifold. So if you used a standard PCV valve, that boost pressure would violently push backward through the valve, instantly overpressurizing the crankcase and blowing your seals sky high. Because of that exact problem, turbo engines absolutely require specialized dual-path check valves or pressure-regulating valves that are specifically calibrated to handle boost and stop that reverse pressurization. On top of that, under heavy boost, blow-by rates just skyrocket and they carry a really heavy oil mist with them. This is why turbocharged applications often require dedicated air-oil separators. You guys probably know them as catch cans. These are absolutely essential. If that oil mist coats the turbo's compressor inlet, it completely ruins its efficiency. And for direct injection or GDI engines, where fuel isn't washing over the back of the intake valves, that oil mist will rapidly bake into thick, power-robbing carbon deposits. Definitely not what you want. Let's jump into Section 4, Field Diagnostics and Testing. All right, grab your tools. It is time to build your diagnostic flowchart. As a junior mechanic, you really need to master this if-then troubleshooting mindset by interpreting fuel trim data. Modern engine control units strictly monitor PCV flow, so if a PCV valve gets stuck wide open or a hose fractures, the engine starts pulling in unmetered atmospheric air. That's going to show up on your scanner as OBD2 codes P0171 or P0174, meaning the system is running too lean, and you'll usually get a rough or surging idle with it. Now, if you see a P0507 for abnormally high idle RPM, that tells you a mechanically compromised valve is creating an uninterrupted vacuum leak that's bypassing the throttle body entirely. And if you hear a hissing noise, you are definitely hunting for a cracked hose or a failed rubber grommet. So let's see how this builds into our physical checks with the classic rattle and vacuum tests. Step 1, pull the mechanical PCV valve right out of its seat. Step 2, shake it right next to your ear. You want to hear a really sharp metallic click as the spring and pintle move around. If you hear a muted thud or literally nothing at all, that internal pintle is completely seized up with carbon lacquer and the valve is totally dead. Throw it out. Step 3, reinstall a known good valve, idle the engine, and pull the open end off. Step 4, place your thumb over it or hook up a vacuum gauge to identify any internal valve sticking. You should feel a very strong vacuum pull against your skin or see a steady draw on the gauge. If you don't feel that suction, it means your hoses or manifold ports are totally choked up with sludge. For a highly accurate health check, we use a manometer. First, get the engine idling at normal operating temp. Second, connect a high-precision magnehelic manometer directly to the oil dipstick tube. This lets you read the ambient pressure inside the crankcase. Third, what you're looking for is a slight, stable negative vacuum, typically somewhere around -0.1 to -0.5 inches of water. That confirms the system is actively sweeping the crankcase. But if that gauge registers positive pressure, that is definitive proof of a complete restriction in the system, or excessive piston ring blow-by that has just completely overwhelmed the whole ventilation circuit. And our final section, Section 5, Service Intervals and Replacement. Let's cover routine maintenance and exactly what you should be looking for during a standard oil change. Because remember, the valves aren't the only failure points. You have to inspect the rubber hoses too. You are searching for hidden cracks, particularly on the underside of the hose where heat cycles do the most damage. Check for hardening and extreme brittleness. Like if it snaps when you bend it, it's done for. Watch the hoses while the engine is actually running to check for inner collapse under heavy vacuum loads. Also, give the hose a squeeze. If it has a spongy texture, it has reached oil saturation. The rubber is literally degrading from the inside out and will fail soon, which will totally ruin the closed loop circuit. When it is finally time for a replacement, follow these safe procedures. First, be incredibly careful when removing a stuck PCV valve. These things live in extreme heat, and the plastic becomes incredibly brittle. If you shatter it, you are going to be spending your afternoon fishing plastic shards out of the valve cover. Second, inspect the rubber seating grounded. If it's deformed at all, it'll cause a vacuum leak. Third, if the vehicle has serviceable valve cover oil baffles, safely flush them with solvent, but be extremely careful not to damage the delicate internal wire mesh that separates the liquid oil. And fourth, always check the intake manifold port. If you see heavy oil pulling in there, you must clean it out to prevent engine misfires and severe carbon buildup. Let's summarize everything into a quick, highly actionable shop maintenance list. You should be inspecting the valve and hoses every 20,000 to 30,000 miles. Honestly, don't even wait for failure. Proactively replace the PCV valve every 30,000 to 60,000 miles. If your client is running an aftermarket or OEM catch can, make sure you empty it every 3,000 to 5,000 miles. Here's a critical note. Always check for application-specific flow ratings. A 2.0-liter 4-cylinder valve flows very differently than a 6.2-liter V8 unit. Never just slap a generic valve on there. And lastly, if you complete a PCV repair and spot milky sludge in the system, you absolutely must change that engine oil immediately to protect those bearings. So, I'll leave you with this provocative thought as we wrap up today's explainer. Could a neglected $2 plastic valve be the real reason your next engine blows a main seal? I mean, think about it. The next time you have a car on the lift for a routine oil leak, don't just immediately patch the seal. Check the PCV system first. You might just save an entire engine.